So let's not sure why it quit on us when I just blanked the screen. Oh, this could be the reason. So here we go. We start off with our differential equation. We call this vector, we call the vector u x and y. So let me make this a little bigger. Okay. So this is just the stuff we've been talking about. And the reason why I use alpha and beta over here is because I've got a and b over there. But when you actually read theorem 8.4 in your text, it will have a and b here because I haven't talked about in there just before the theorem the structure of that problem. It's further back in the textbook, so you won't get confused with the fact that we're reusing a and b in a different context. But seeing this is all on the same page, I changed it around. So now we have an example which we talked about. And remember we talked about models, compartment models, in which we have different compartments. And we talked about flows into compartments and flows out of compartments. And then maybe this flow goes into the next compartment and comes out. And then maybe it just goes into the next. And if you do that, then you can write down certain kinds of models. Now in this one, we just have your blood and your brain and the blood-brain barrier. And we have some kind of chemical like morphine in the blood that goes through to the brain. And we're interested in what the concentration of morphine is in your brain, because in your blood it's not really acting where it should be acting, but you don't want too much in your brain at once, because that's not going to have the right effect. So you have to know how it distributes to the brain. So one can do experiments. People can do experiments with animals and inject into the blood and then take out at fixed points in time every 10 minutes, whatever, a small sample from the blood and the brain, and they can estimate the rates. And so if x of t is the amount of morphine in the blood, t hours after the injection, and y of t is the amount of morphine in the brain, then you can say assume the rate at which we go from the blood to the brain is proportional to half the concentration in the blood, and that the rate at which, in each unit of time, it's cleared from the brain is proportional to 1/10 of the concentration that's in the brain. If you write down this equation, then this is what's in the blood, and in each unit of time, half the proportion in the blood is leaving the blood, and that half is going into the brain. And then a tenth of the proportion in the brain is being excreted and going somewhere else. Or it may not be excreted, it may just be broken down into other products that are no longer morphine. So that's what's happening. So here we have a model, and then if I say to you, what happens if I initially inject 6 units of morphine into your blood and we start you out at time 0? Well, if you calculate the eigenvalue and eigenvector, now here's a little secret it's not a secret, a little help thing. If you have a diagonal matrix, what does a diagonal matrix look like? A diagonal matrix looks like this. I'm going to draw what's called a lower diagonal matrix, but you can also have an upper diagonal matrix. A diagonal matrix has elements on the diagonal, and a lower diagonal matrix means that it has elements in the lower part, and so on. But that all the elements in the upper part are 0. So if all the elements in the upper part are 0, and then most of the elements in the lower part are non-zero, then we say this is a lower diagonal matrix. Now the reason why that's important is that you can show this, and you don't have to do it for this class, that the eigenvalues of a lower diagonal matrix are its diagonal elements. So it's very easy. You don't have to go solve it. You can just read them off. If you look at this matrix over here, the matrix A, is it a lower diagonal matrix? Well, since it's got so few elements, it's kind of trivial. It has a diagonal element. The lower diagonal element is filled in, and the upper diagonal element is not. It's 0. So we say, yeah, that's a lower diagonal matrix. And this is also true if it's an upper diagonal matrix. So if this was 0 and this was not 0, then immediately you could know that the eigenvalues are just those two numbers. In a 3 by 3 matrix, yeah. It can be anything. It doesn't affect the fact that the eigenvalue. What you can do is you could work through this. Do you want me to do it? Okay. So how would we? I'm just going to do it in 2 dimensions. So here I've got a matrix A, and I'm going to say this matrix A is equal to A, B, 0, C. So now I'm going to find the eigenvalues. So A minus lambda I is equal to 0. So that would be A minus lambda 0, C, B minus lambda is equal to 0. So A minus lambda I would be written as this. Now the equation, the determinant of A minus lambda I would be equal to A minus lambda times B minus lambda times minus C times 0 equal to 0. Now because it's C times 0, this is always equal to 0. It doesn't matter what the value of C is. So if this is always equal to 0, then A minus lambda, B minus lambda is equal to 0 means that lambda is equal to A or lambda is equal to B. So it doesn't matter what the value of C is, it's nullified in the equation by the fact that you're taking C and multiplying it by 0 to get the eigenvalue, or what's called the characteristic equation. So in 2 dimensions, you just see, it falls out straight away. Now, you can go through this in 3 dimensions, and you can show that. That's what happens in 3 dimensions. I'm not going to do it, but if there's anybody who's keen to do it, go ahead. Okay. So now, we know that the eigenvalues are -1/2 and -1/10. Now, this particular example there's some earlier theory that we said that if you have a triangular matrix in general, and you've got an alpha and a beta and a gamma in there, then this is generally how the eigenvalue would look, the eigenvector would look. But I'm not going to go through that theory. You can read it in the textbook or not. But you can solve this straight away. And you can say, okay, if the eigenvalue is -1/2, then you can show that the eigenvector can be written as -0.8 and 1. And you can also show that if the eigenvalue is -1/10, then the eigenvector can be written as 0 or 1. Do you want me to do that or not? Yeah? It doesn't matter. When we write down our theory and we say, okay, we're going to call the dominant eigenvalue, like in the Leslie matrix theory, we're going to calculate all the lambdas. I'm going to call them lambda 1, lambda 2. And maybe I'll find out that lambda 5 is positive and dominant. Then I'm going to change its name. I'm going to call it lambda 1. So you can always, it doesn't matter what you call it. And when we have a theorem, we'll say, there exists a dominant eigenvalue, and we'll call it lambda 1. So when I solve this, I'm going to say lambda 1 is A, or I'm going to say lambda 1 is B. And then lambda 2 is the other one. That's fine. So now, if we write down our solution in terms of eigenvalues and eigenvectors, well, firstly, to solve for the coefficients A and B that determine the initial conditions, then we'll say when t is equal to 0 and t is equal to 0, the equation reduces to, remember the initial condition in this case is the vector 6, 0. That's because at the start, I'm injecting 6 units of morphine into the blood and nothing into the brain. So that's why it starts out as 6, 0. So now, in order to get the initial condition, I go to the solution and I say when t is equal to 0, I get 6 is equal to 0.8 times A plus 0 times B. So this is 0 times B. And here, 6, 0, 1 times A and 1 times B. Okay? So, when I solve that for A and B, I get A is equal to minus 7.5 and B is equal to 7.5. That's just 2 equations and 2 unknowns to solve them. So that means the solution can be written as minus 7.5 times e to the minus a half t. A half is my first eigenvalue. Its corresponding eigenvector is this. Plus 7.5, which is my second constant, times e to the minus, this is my second eigenvalue, 1/10 t. And the second eigenvector is 0, 1. So that means this is a number times a vector, or scalar times a vector. So that means the first equation would be this times that, which gives me this, plus 0 times that. So that's why I don't have a term there. Now 1 times this is just this term, and 1 times that, well, actually, I've changed them around. 1 times this is this term over here, and 1 times that is this term over here. So you can see that U1, the first U1, which is the amount in the blood, is going to satisfy this equation, and U2, the amount in the brain, is going to satisfy this equation. And when t is equal to 0, we just get 6, where we're supposed to start at. And this is 7.5 minus 7.5 is 0, where we're supposed to start at. And now we can just plot those curves using a graphing program that can calculate exponentials. On the other hand, if we made a model, if we went to NOVA and we said, okay, we're going to build this equation in NOVA, and we're going to put these values in for A and the initial value of U, then we don't have to do all this theory. We're just going to go to NOVA. We're going to build our NOVA model. We're going to have our 2 variables. So let me build a NOVA model in blue here. So this we'll call U1. This we'll call U2. And then we'll have our NOVA model. And then we put the constants in, and we put the initial conditions in, and we just simulate this. And if we do that, NOVA will produce these curves. So you have 2 ways of generating these curves if you have a linear system. That is, you can say, I can do the theory. I know the solution can be expressed in terms of the eigenvalues and eigenvectors. I can calculate and find the solution. If I do this, I'm still not entirely there because I'll come up with this answer. Now I say, how do I know what that looks like? Because in the end, I don't know what's going on until I draw it. Unless you really, really have an intuitive feel for what this is going to do. Very few people would have it. I don't. So I have to draw it. So then you have to go to a graphing calculator. So at some point, you have to do a numerical computation. You can either do a numerical computation that draws the solution because you know using exponential functions in a graphing calculator, or you can simulate the model, and you can simulate the solution. Okay? So here's a way where you can do it 2 different ways. But in most cases, if you go to systems that are not linear, when a system is not linear, then you don't have a theory. Then you have to use the computation. Okay? So there's an example in the textbook on source sink dynamics and blackbirds. So very often in ecology, there's this idea of source sink dynamics. And the idea of source sink dynamics is that you have what is called a metapopulation. Does anybody know what a metapopulation is? Has anybody heard of that term? Who's heard of it? Okay, just a couple. Anybody want to tell me what they think it is? Yeah, so in fact, when we say there's a population, that's an idealization of the fact that populations actually have more structure spatially. And you could say the United States essentially consists of, or California is essentially 3 meta-populations with some small residuals. So there's kind of a conglomerate of individuals in the Bay Area, then in Los Angeles, and then down in San Diego. And in each of these populations, people are interacting, but then there are people traveling between them. And in fact, the world is kind of an artificial meta-population. Because every country, you can say, has a boundary around it, and you can't mix freely with people in other countries. And now it's getting so bad that New Jersey is a meta-population. And if you go to the state of New Jersey and you're a healthcare worker coming back from West Africa, then they can put you in quarantine, and you're not allowed to move around at all. So you can't go to New York, and you can't even mix with the people in New Jersey. But anyway, in ecology, you very often, typically, for example, if there are species that live at high elevations, and you look at the Sierras, then each mountain peak represents a high elevation population, and individuals can maybe move between them, but they don't like to be at lower elevations, and they just move through to the higher elevation and settle there. So a metapopulation, you can kind of represent as a number of circles like this, where individuals move freely within here, and then there's movement between, but the movement between these populations is at a much lower rate than within the population. So in a metapopulation, if you're going to meet up with somebody, you've got a random chance of just meeting anybody within inside a local population. Sometimes that might be called a deme. Has anybody come across the term deme? It's kind of a word from genetics, which means a local population. And then individuals move, and so the whole population has the structure. Now, within a metapopulation, ecologists say sometimes, if we were to shut off these connections, if we were to cut off connections like that, then the population within here may grow or decline. If the population is growing, if the population can grow in here, we call it a source. But if, on its own, it declines, we call it a sink. So if we cut everything, what would happen is the population would disappear here, but it would maintain itself there. But if they're connected, even though the population is declining over here, because it's growing over here and individuals are moving in over here, we might always be able to find a population there. So this doesn't go extinct. It manages to persist because it's fed by immigration from other areas. So kind of on a grand scale, this is what's happening in places like Italy and Germany. In Italy and Germany, the population is not actually replacing itself. Population numbers are going down slowly, same in Japan. And if you were to stop immigration to those countries, those populations slowly decline. However, there are countries where populations are growing, like in Africa, and so they're being fed by immigrants. The United States has a fairly vigorous growth compared to Europe, and it has a small internal growth rate, but it's got an additional growth rate that comes from immigration. So when we talk about immigration reform and that we should limit it, we also need to think about the fact that economically, this country can grow more vigorously because it's got immigrants coming in. However, what the politicians are trying to do is have selective immigration. So they say, okay, well, we'll take people who are well qualified that we need, people like IT people, people like nurses, and so on. And so what happens is that the United States is a sink in terms of nurses. Like if we didn't allow people to come into the nursing profession from outside, the number of nurses per 100,000 people would slowly go down. And there are places where there's a source. It was very interesting. I once spoke to a woman who was from Asia, and I was saying, I was on an airplane, and she said, she's coming to interview for a job up in Northern California to be a nurse. And the hospital there, the Kaiser system, was going out to Asian countries and recruiting people and saying, we'll pay for you to come over and interview, and we'll get you an H-1 visa. And actually, we're taking medical personnel out of countries that need those medical personnel. And then now, when there's an Ebola crisis, we're providing this huge disincentive for some of these people who may have come to this country some way back, work in our medical healthcare industry, now feel they need to go back. They go back there, they're going to come back. And we think of punishing them by isolating them for 3 weeks, when there's no medical reason to isolate them. It's just because people are fearful. What they fear is that these individuals, either they don't trust the medical profession who says these people are not contagious, or they don't believe these people will behave appropriately. That is, take their temperature every day, and if they measure that they've got a temperature, they will actually then go to the hospital and be tested and possibly isolated. So if you know how to do all this kind of modeling, you can model the following scenario. You can say, okay, if we send medical people to Africa now, and we assume that they have an effect on reducing the epidemic, and maybe we can build a model, maybe we can predict that if we send the right number of people and they're able to isolate individuals and detect cases soon enough and treat these individuals appropriately, we should be able to